Hello everyone, my name is Việt Dũng Nguyen. I am a PhD candidate at Rochester Institute of Technology and the Neuroadaptive Computing Laboratory. When we start building AI systems, whether it's object detection, language models, or a custom training pipeline, we actually start very small. We develop on a single GPU or a local workstation, but as your data grows and the models become more complex, that local setup becomes a bottleneck. So to move from a prototype to a production-grade AI, you need to scale. In this talk, we are diving into the world of high-performance computing, or HPC. We will look at how to leverage HPC clusters to scale up AI systems and manage massive training pipelines. So, to achieve this, we want to learn a thing called SLURM, or Simple Linux Utility for Resource Management. To work with SLURM, we need to be able to understand Linux, Bash, and SSH. We also need to understand distributed computing theory as well. So I'll be talking about those two parts, but feel free to skip over the high-speed computing parts if you already know. I'll then try to demo the multi-trial job summation script and demo the sharded data parallel job summation script. And finally, I'll show you tips and tricks of how queuing system works, Conda, and file transfer using FileZilla. First, I will go through the overview of Linux, Bash, and SSH. For Windows users, you might want to test out Linux with Windows Subsystem for Linux or WSL. So in Linux file system, we use / to separate folders instead of / like in Windows, like this. Instead of using the mouse to click, find, and open them, you type commands into the terminal to tell the computer what to do. Here are some examples of commands that can be used in the terminal. First of all, clear is clear the terminal. pwd is print work directory. ls is list files in the current work directory. cd is change directory. rm remove. And tilde is going to home directory. And slash is the root directory of the operating system. The dot represents the current working folder. And the dot represents the parent directory in relative path. And then finally, we can represent a path with an absolute path starting from the root directory. Here are some other frequently used commands. Cat, view the file. mkdir, which is make directory. This is to create a folder if you want to create a folder. Notice the -p there. It's basically if we are creating a folder with the subfolders inside, we have to pass -p in. Next is rmdir, which basically remove folder. This folder has to be empty in order to be removed. Next is head-n3 file. Basically, you're trying to view the file where the first 3 lines will appear in the terminal. Next is tail-n3, basically viewing the last 3 lines of the file. Next, touch file, which is basically creating file. cp is copy, we're copying a file from the source to the destination. mv is moving, so we're trying to move the file from source to the destination. Next is rm file, which is removing a file. We can use this in place of rmdir. This rm command has more utilities and can be used to recursively remove a file or a folder. If we want to remove multiple files in a single folder, you can pass the folder in with the -rf option. The R meaning recursive and the F meaning force. Please note that we should not do rm-rf/ because if we do that, we will remove the whole operating system, resulting in a corrupted operating system or corrupted Linux. Next is grep pattern file. Basically, we're trying to search a pattern in a file. Next is man command, which is printing the command manual, basically printing out the instruction of how to use the command. Next is du-h dot, basically lists all items and size of the current folder. Note the dot here is the current folder. Since we're specifying max depth is 1, it will be no recursive. For this tutorial, I'll be using VS Code for convenience. Here's the link to download and set up. First of all, I'll be demoing how to write a bash script with variables, comments, loops, conditionals, and operators. First of all, I create a bash script with the postfix.sh, so there are several different things we can try. First of all is echo, a string, right? This is to print out to the terminal. Next, we define a variable, name is equal to John, which is basically we're trying to define a string. And then we echo that name variable using the $sign. Remember, variable names are case sensitive, so the variable name with the n is not capitalized will be different from the variable name with the n capitalized. Name with the n not capitalized is assigned to John, and the name with the n capitalized is assigned to Jane. So we can see we have successfully created the variables and refer to the name John. Next is numeric variables. Basically, Bash treats everything as strings by default, so even if we put a number here, it is still understood as a string. So in this case, we have to cast them to a number. We do this by using parentheses. And if we want to add two numbers together, we can add them inside the parentheses like this. And then finally, we print out the sum. Next is environment variables. Before we are running the Bash scripts, there is some global environment variables that is predefined for us, so we can refer to. First of all is $user, next is $home, third is $pwd, basically your username, your home directory, and the current working directory. There are a lot more environment variable as long as you defined it. We can also use the Bash script to reach from the user terminal or user input. Basically we type read-p and then we save to the variable username. And then now we echo or print out to the terminal, nice to meet you, $username to refer to that variable. Now for example, my name is Viet, and it will return the print line, right? Nice to meet you, Viet. And then we can also have special variables in here as an environment variables. Double $signs is the process ID, and $random is to generate a random number. Next, we are going to talk about the arguments of the Bash file that can be used to pass into the command line arguments. The arguments of a Bash file is denoted as $number, starting from 0. To get the number of the arguments, we use $pound. Here I pass in full as the first variable, bar as the second variable, and hello as the third variable. Let's run it. We can see that the first argument is full, second argument is bar, and number of arguments is 3. Next is conditionals. We can specify the if else, if then else, if else if statements like so. Please note that you need to put the condition inside the brackets for the if conditions to work. For the signs, we use -gt for greater than, -equi for equal, -lt for less than, -le for less than or equal to, -ge for greater than equal to, and -ne for not equal. And finally, when we're comparing a variable to a string, we just use a single equal. As you can see, we've successfully do the if conditions. Next is loop. There are 3 kinds of loops in Bash. First of all is for loop, second is while loop, and third is for loop with range. For loops, we just need to specify the array of number. For example, in this case, 1, 2, 3, 4, 5. For while loop, we need to put the conditions inside the bracket. The condition is similar to the if-else conditions. For loop with range, we need to put the range inside the curly braces. And please note that this range is inclusive. And let's run it. Next is function. In Bash, they allow us to write functions similar to other languages as well. We first start with the function name, and then double parentheses, and then curly braces, and then the body inside. Please note that when we pass the arguments in, they are similar to the Bash command line's arguments. $number. For example, if we want to create a function called add, we need to take the first 2 numbers from the command line's arguments, and then finally we print out the results to the terminal. To call the function, we can write $, parentheses, name of the functions, and the arguments that we passed in. Finally, we print out the sum of the function. Let's run it. Finally, we are going through the operators of the Bash. In here, I take the 2 examples, A is 10 and B is 3. To compute 2 numbers, we use double parentheses and then put the operations in there. For example, A plus B, A minus B, A multiply with B, A divide B, and A modulus B. For conditions, we are going to use -gt, -eq, and so on. For string comparison, we are going to use the name of the variable with the equal sign and the string that we are going to compare to. If we want to check the string is empty or not, we can use -z followed by the string. Let's run it. So next I want to talk a little bit about SSH or Secure Shell Scripting. SSH works on a concept where securely accessed remote server can use a public key and a private key to work. So a public key in this case is like a lock that everyone can see. The private key is like a key in the holder's hand, so only the holder having the key can unlock and access the server. And typically, most research cluster servers use SSH to allow the user to access the server from remote. There are many tools that we can use to connect to the server through SSH. For example, on Windows there's MobileXterm or OpenSSH and so on. On Linux, we can just use the terminal. We can also use VS Code to access the server through SSH. So now, part 2, distributed computing overview. So first of all, I want to demonstrate different examples of parallelism and concurrency. The first case is no concurrency, no parallelism. In this case, we are going to do each task synchronously, which means that we can only reach task 2 after we finish task 1. So the advantage of this is very simple implementation, but the disadvantage of this is the method is very slow, monotone, and not parallelizable. Here is the demo of no concurrency, no parallelism, and sequential execution. In this case, I'll try to run tasks sequentially on a single thread or process and measure the time it takes. I run the task 3 times and compute the total amount of times the task consumes. The task is very simple. It is basically sleeping for 1 single second with printing out the task ID. And finally, let's run it. We can see that the task is completed in sequence. No concurrency, no parallelism. Next, we're going to talk about a different case, which is concurrency this time, but still no parallelism. The theory is, in waiting for a task, we're trying to do another task. And then after we finish that task, we come back. This is also very similar to JavaScript's async await functionality. As we can see in here, we are trying to reach the task 1, but the task 1 requires us to wait for a bit. Then we switch gears to the task 2 until we finish waiting, and we come back and continue the task 1 again, and then we continue doing task 2. So the advantage of this method is that it is very faster than no concurrency, and we can spend some amount of time when we're trying to wait for a task to do another task. The disadvantage of this method is basically some tasks are too long and they're trying to block the execution of the other tasks. Here's the code with asynchronous concurrency demonstration. In this case, I am trying to running it with the async IO library. I define an array of async tasks with different task number from 0 to 2. And I call await async IO.gather all tasks, which basically wait for all tasks to finish, and then I record the total amount of time spent throughout the whole processes. The async tag is very simple. We just called async IO.sleep and then we await. When we are awaiting the async IO.sleep duration, the process is allowed to switch gear to the other task that they are trying to do. This will save us some time and we do not have to freeze the CPU when we are waiting for a single task to complete. Now let's run it. We can see that the total time it takes for async task to complete is 1 second instead of 3 seconds, like in synchronous tasks, no concurrency, no parallel. So now I want to demonstrate the case of concurrency and parallelism. If concurrency is async and await to perform the task more efficiently on a single GPU or a CPU, then parallelism is utilizing multiple CPU or GPU at the same time. Either you can do sequential tasks or you can do asynchronous tasks. So the advantage of this is that we can parallelize tasks that can be done separately. Let's go to the code. So here's the code to demonstrate the concurrency and parallelism, which is using multiple processes that is running concurrently. In this case, I will create 3 simple tasks on a 3 different process, and then finally append the results to the future array. After that, I wait for all the results to complete, and then record the time. Let's run it. We can see that the machine spawned 3 tasks at the same time, or spawned 3 processes at the same time, and those 3 processes can start asynchronously, leaving the total time of 1.02 seconds, which is way lower than 3 seconds in sequential task completion. Next, I'll be going over sharding. So sharding is a technique that is typically done to separate the models if the model is too large. It is the process of breaking a task down to multiple subtasks and aggregate them when the computation are done. In other words, it is a technique for splitting large datasets or workloads into smaller, more manageable pieces called shards. that can be distributed across multiple machines and processes. So each shard holds only a subset of the total data, and together, all shards represents the complete dataset. We can also apply sharding with concurrency and parallelism. In this case, each task is split into different subtasks, and each subtask is solved using a dedicated device, CPU, GPU, or node. The advantage of this is this method has concurrency, has parallelism, and this also allows multiple devices to solve multiple tasks while minimizing the idle time. So here's an example of a sharding. First, I create a NumPy matrix of size 1000 by 1000 with a random number. I want to divide the NumPy matrix into 4 shards by using the shard matrix function. In this case, we are only trying to divide in the row dimension. Next, we are comparing between sequential processing of shards and parallel processing of shards. For sequential processing, we simply pass the processed shards into a for loop and then append the results to the sequential results final array. And finally, we record the time it takes for the sequential processing. For parallel processing, we also record the times, and we use the same process pool executor, and we map the processed shards to the executor. Finally, we also record the time it takes for the multi-processes to be finished. The process chart is very simple. We simply mimic the CPU-intensive computation by doing multiple operations. In this case, I'll do a for loop of 10 times, computing the sine and cosines of the results before adding them together and square it, and then do a square root of its absolute value. Finally, I compute the sum of the results in a single scalar. So let's run it. We can see that parallel processing for sharding is also faster than sequential computation. Okay, so we are getting closer to a distributed system that allows us to understand the structure of a SLURM cluster. So the definition of a distributed system is a collection of independent hardware and software code nodes that is usually connected together in a network system. So each node has an independent number of processors and no shared clock. They also don't share memory as well. And processes are autonomous and executed concurrently throughout each node. Think of nodes like different computer that has different processors in there, different number of GPUs in there, and different number of CPUs in there as well. So the purpose of this is to use multiple nodes to solve a very large task that requires multiple computers to calculate. On some cluster, each node will have from 0 to 4 plus GPUs, but normally they will have 4 GPUs. Part 3, high performance computing. For example, if you are training a large language model or a computer vision model, you can train it on the SLURM cluster. To achieve this, we need to tell SLURM what resource we need, and we have to create an SBatch script. In this script, there will be configurations such as the number of nodes need to be used, the number of tasks used, what type of GPU it is, how many VRAM do we have to use, and so on. So here is the structure of a SLURM script. The first line is required. It is also called shebang line. To define the configurations for a SLURM script, we have to use bash comment. For example, this is my first configuration, this is my second configuration, and so on. And then finally, we specify the bash code that we're actually running here. Here's an example of an SBatch configuration file. First of all, we need to specify the job name. We can also specify the comments as well, but this is optional. Normally on SLURM cluster, we also need to specify the accounts, but please check with your SLURM cluster server to see more details. We also need to specify the partition, the maximum running time. Next, we want to define the files that the output of the terminal and the arrow go to. In this case, X is the job name and J is job ID number. The job name is the name that you specify, and the job ID number is the automatically generated number on the SLURM cluster. You can also use Slack configurations, but this is totally optional. We can also specify the number of nodes that we want to use, or in other words, we are trying to have how many computer or machine that we are trying to use. In this case, I'll be specifying as 1. Next, we have to specify the task configurations. We need to define the number of tasks. Think of tasks as a number of processes. In this case, the n task is equal to 2. Basically, we're trying to run 2 tasks in total. Next, we have to define the number of tasks per node. Since we are using only one node, we will run the total number of 2 tasks inside a single node. That's why the number of tasks per node is 2. Next, we need to define the CPU and GPU configurations. In this case, I define the number of CPUs per task is 4, and we're using the GPU A100 and the number of GPU per task is 1, which is basically asking for 2 A100 GPU in total. Finally, we have to define the memory configurations. You can either set memory per node or memory per GPU or CPU. Please make sure you tune this to the reasonable amounts that your task is requiring. So after defining every single configurations, this is the piece of code that needs to be run. First of all, I will include the job name and the job ID and the host name as well, the date and the working directory. Notice all these variables, SLURM job num nodes, SLURM CPU per task, and so on, is passed in as environment variable when the SLURM cluster run out tasks. Finally, I put a sleep for 10 seconds to mimic actual computation. Finally, I print the date for the job completed out. Here is an example of a bash job submission script. First of all, I define all the configurations, and then I run it using srun bash commands. First, I define the job name, the comments, the accounts, the partition, the output files of the terminal and the arrow. The time limit is 30 seconds. I use 1 node, 2 processes, and 2 CPU per task. Finally, 10 megabytes per CPU. What I run is basically I try to print out the task ID and the total number of tasks. And then I sleep for 10 seconds to mimic the actual computation in the real script. And this script can be a Python script, can be model rendering script. It can also be a large language model training script as well. So let's run it. I am currently on the SLURM cluster server, and I will try running the example file. In order to submit the bash job, we are going to call sbatch 03 example.sh, and the bash job has been submitted. So in order to observe the output, we need to check the output file. We can see that there are 2 files, one for arrow and one for output of the terminal. Let's check those out. We can see that there is no arrow, which is good. And here's the output. This is the host name. This is the task number. We can actually see that we have successfully run 2 processes. The first process with the task ID 0 and the second process with the task ID of 1. And the total number of tasks or processes is 2. Note that we can also submit a bash script using sbatch and specify the configuration through all these parameters or command lines arguments, and then finally passing the running file or the executable file at the end. Now I will demonstrate a bash job submission case that we use multiple nodes to do multiple trials of the same task. In this case, I will be doing 2 trials. For each trial, we are going to compose the executable. In the compose executables, basically it is a bash file, and then I called python compute.py and with the trial to the Python file. And then I returned the command and the experiment name. In the compute.py file, it is doing a lot of computational simulations. For example, Monte Carlo pi estimation and matrix operations. This is done to mimic the computational complexity of an actual run. Finally, I print the bash string out and then export that to a command.log file. And then I submit the job through sbatch with all these configurations. And then finally a call to a command.log file. Let's run it. So I have successfully submitted 2 bash jobs. Now let's check the output files, which resides in the logs folder that I have specified. So we can see that there is 2 experiments, and each experiment has 2 files, which is an arrow file and an output file. Let's check each of them. We can see that there is no arrow in the first experiment, and we can see the result is printed out on the output file of the first experiment with the trial ID is 0. Basically the first experiment, or the experiment 0. Similarly, there is no arrow in the experiment 1, and the results of the experiment 1 is completed. You can see that's the trial ID is 1, which basically the second experiment. Next, I'll demonstrate the working of a job submission that runs multiple tasks, and each task solves 1 shard in a total of 2 shards at the same time. Notice that when I compute the executable, I also pass in the command line srun python shard.py, and I pass in the number of shards, which is 2 in this case. And then finally, I write the bash commands to command.log, calling sbatch again with the number of configurations, and then passing the command.log file into the submission process.call. Regarding the shard.py file, it is basically trying to grab the shard and compute it, and then return. Finally, aggregate the results together with the other task. First, I get the corresponding shard data from the 1000 by 1000 matrix with respect to this shard ID. Then I compute the shard results of this specific shard and then append it to the dictionary, and then finally save the shard results in a JSON file. For compute the shard results, I basically compute the shard statistics, the mean, standard deviation, sum, count, mean, and max values inside the shards. And finally, I sleep for 2 seconds to mimic the computational complexity of an actual process. For saving the shard results, I save the dictionary into a JSON file called shard with the shard ID and then results.json. Let's run it. We can see that the job is now done, and then we have the results. Now we have a single experiment coming out, basically one out file, because we're running a single task, not 2 tasks. We can see that there is no error in this file or in this run. In this case, this is the printout of the terminal. We can see that our first task has processed the shard 0 and our second task has processed the shard number 1. The first task processed the data in this from 0 to 500, and the second shard processed the data from 500 to 1000. Now let's check the shard results. These are the JSON file results that we saved in each process. Basically, process 0 save the shard 0 results, and process 1 save the shard 1 results. Let's see each of these files. And finally, it's part 4, tips and tricks. First of all, I will walk you through how queuing system works in a SLURM cluster. If there are so many people using the SLURM cluster, they have to be queued up. So the queuing system works like a priority queue, where a job gets to run first based on some statistics. First of all is fair share, second is age, the third is trackable resource, and the fourth one is partition priority. So age is how long the job has been waiting. If age is higher, then it is more likely to be run sooner. Fair share is your historical usage versus others, basically balance fairness. If your fair share is higher, then your historical usage should be considered more priority. Please note in here that the historical usage fair share point is higher when you're not using that much recently. The third one is trackable resource. If you're requesting fewer number of GPUs, CPUs, nodes, the trackable resources is lower, and lower is better. And the task with the lower number of CPUs, nodes, GPUs will get to be run sooner. The fourth one is partition. So there's different ranking in partition priority. For example, a partition name can be tier 1, tier 2, tier 3, and so on. And the partition with higher tier will be run sooner. Next, I want to show you Conda, the powerful package management system. So basically, the reason why we need to use Conda is because we can isolate the bubbles or the environments for your project. Basically, when you're using Conda, there's no need for admin privileges. So you can install any library you want in your home directory without needing sudo or system permissions. The second thing is you can avoid libraries conflicts. For example, if you're running project A, Python 3.8, and project B with Python 3.12, and project A requires like NumPy 1.2, and project B requires NumPy like 2.0, and potentially there is a conflict between like different libraries, then the code will not run. So that's the reason why we need to separate the environments. So here's basically what you need to do when you're trying to create a Conda environment. First you type conda create -n, and then you specify the name, and then you specify the Python version. In this case, I've named my environment env-name. To activate the environment, we need to type conda activate the environment name. You can see that now there is a prefix of environment name before the host, which means that you have successfully activated the environment called env-name. Now you can install any libraries that you want as normal. To remove the environment, we need to type conda env remove -n and then your environment name. But in this case, I cannot remove the current environment because it is currently being activated. So I need to change to the other environment before removing. Note that in here, I type conda activate to activate the base environment, and then finally I can remove. Type yes, and yes. Now you have successfully removed the conda environment. Note that when I do conda activate my environment again, it cannot find the environment called env-name because I have already removed it. Okay, so now I will walk you through how to use FileZilla to transfer a file from remote to local and from local to remote. Basically, FileZilla works on the concept of SFTP. Basically, it's a protocol that can be used to fast forward the file transfer. In order to connect to the server to download files or upload files, we need to connect to the host. The host will start with SFTP : with the corresponding hostname. You also need to enter the username if needed, and your password as well. Enter the port if needed, and then click Quick Connect. To download the file, you just need to drag the file from the remote site to the local site. To upload the file, you just need to drag the file from the local site to the remote site. And that's it for the tutorial. Thank you very much for listening. If you have any question, please feel free to ask me.